Okay, now we continue with a talk from Nathalie Jones about GPy data.
Aloha ko o Nathalie Jones ko inoa. No Hawaii mai au a me kanaka maoli au. A graduate student at Northwestern University o Jason Wong. Hello everyone, my name is Nathalie Jones. I am originally from Honolulu, Hawaii. I'm native Hawaiian. I am a graduate student at Northwestern University working with Jason Wong. One of the many. So yes, today I have the privilege of talking about GPy before Bruce McIntosh, which I don't know who's scheduled that. But anyway, before I get started, I want to shout out my group, the entire BOBA group. Nothing I do scientifically is possible without help from the wonderful people that I get to work with every day. I also want to say a big thank you to the main collaborators on my paper, Eric, Rob, Annie, and Bill, as well as to the, I think the number is 48 other co-authors on my paper. So if I haven't met you yet, I will do my best to do so. Okay, so what is GPy? You all may be really surprised, but it was an imaging instrument designed to look for young giant exoplanets. And so GPy was based at Gemini South. Actually, I think it might be 2013 and 2019. And yeah, it had all these fun things like an integral field spectrograph, meaning we got images and spectra. Just like we heard previously, it had AO capabilities, and of course, a LEO coronagraph. With the instrument, the team carried out a 600-star survey looking for giant planets and brown dwarfs. Some of the goals of the survey were to measure planet occurrence rate, get some atmosphere spectra, and obtain orbital properties. And this is an example of what a GPy H-band spectrum looks like. Okay, so Eric and the team in 2019 published the first half of the survey, kind of gave some results. So in this tongue plot here, which is in semi-major axis and mass space, they were able to show the detected objects and kind of show how low of a mass threshold, good Lord, that's hard to say, they were able to reach within the first half of the survey. And in general, right, for our direct imaging survey, we want to understand two things, right? Of course, we want to understand like the planet population we are studying, but we also want to understand statistics about the survey itself and get to know the sensitivity of the instrument. So main tool in this work is contrast curves. So this is a real GPy contrast curve of 51 area B. And the idea is below this line, we are not sensitive to anything, right? We can't say what it is. However, everything above the line, we want to know exactly what it is, and that is kind of what my work has been about. So the first step was that I needed to look at my sample of candidates from the GPy data. So we have blobs that we want to know what they are above our contrast curve, right? So where are these candidates coming from? These are coming from the forward model match filter planet detection algorithm, CJB's 2016 and 2017 papers. So we heard a lot on Tuesday about speckle subtraction. This is not necessarily that. This is a way to forward model the stellar PSF in order to make a guess at what our data looks like with the kind of like error and aberrations part of it. So all of my candidates came from this algorithm. So initially, my job was to just see how many things above 5 sigma the FMMF algorithm detected, and it was way too many for one graduate student. I think you'd need a whole army of Nathalies to be able to go through 300 detections. So I ended up using a threshold initially of 7 sigma, and I found that one Nathalie could work through 30 objects. I ended up reaching a final sample of 12 candidates. I reached a final sample of 12 candidates, kind of culling things down through manual inspection of the images for obvious artifacts and mask effects. Of course, reviewing the literature to see if someone else had figured out what that blob was. I also ended up filtering by separation to the coronagraph with the idea that blobs that are closer into the coronagraph are more likely maybe to be some sort of image artifact or harder for us to determine what they actually are. And the last thing that I did, which was really fun, now meeting all of you, was dig through your notes from 10 years ago and to try to put together the picture of what was going on and as you were all observing. Okay, and so I like to think of this task, this final task, of assigning a status for each object, like a traffic light. So if we determine that this object is a background star, stop, throw it out. Okay, cool. Sometimes the GPy data is not enough alone to figure out definitively what this object is. So, right, we're kind of waiting at a yellow light, we're slowing down, and sometimes you get really lucky and it's a planet, so let's go. Okay, so when I was double checking these blobs from the FMMF algorithm, I had two steps. All right, so the first, if we have multiple epochs of data from GPy, was to look at the common proper motion. So these are background plots, and so these blue, these blue kind of butterfly wings are the areas of a possible orbit. So if these points, like through Keplerian motion and Newtonian, basic physics, if those could possibly make an orbit. And the gray wiggly lines are if this object has really high common proper motion and it's actually something just zooming through the background. So as you can see on the right here, this is the example of a real confirmed planet, and the positions are definitely within the blue zones. However, on this case here, right, the position measurements we have are both on the wiggly line and within the blue zone. So we need more data here. So the next step is, of course, to extract a spectrum and ask the question, does this look more like a star or a planet? So on the top, I have a GPy H-band spectrum of something we determined to be a background star. And on the bottom, I have a real planet. And as you can see, right, the shapes by eye are kind of different. We have kind of like a gentle slope for the background star and more of this like peak situation for the real planet. Obviously, I'm not just eyeballing everything. I performed chi-squared fit tests against star-like models and planet-like models. So the red points here are from Phoenix stellar models, and the blue are either from SPLAT, so empirical data, or the XRM atmosphere models. So as you can see, for the for the background star, the red star models have a smaller chi-squared than the blue planet models. And the opposite is true here for a real planet, right? The star-like models have a higher chi-squared than the blue planet models. Okay, but sometimes you need more data. Sometimes the background track plots and our spectra aren't quite enough, and you need to get more data. This happened to us last summer. We ended up finding a brand new directly imaged exoplanet, HD 143811 ABB. So I have the two epochs from GPy here in blue, and like I said, this is a case where additional data is necessary. So we also found an archival epoch from Keck-Nurk 2. So I think I want to point out like why am I doing this and why this is important. As you can see here in this 2016 epoch, they actually got a pretty good detection. And again, because I dug through all your notes, you guys were all like, wait, we should look at this again. This looks promising. But it wasn't followed up until 2019. And I don't know why everyone keeps using this picture over this one, because the data from 2019 is really bad. It was like a very low signal to noise detection. It was really messy. So that is why you have a little graduate student going back through the data, because sometimes our algorithms don't catch these things. So yes, this is actually the second planet discovered with GPy, and it was also simultaneously confirmed by a team led by Vito Squicciarini last year. So hello, he's on Zoom, I think. And not only is this object exciting because it's the second GPy planet, this object also orbits a tight spectroscopic binary, which is only one of a few that we've been able to image. And if you would like to know more about the spectroscopic binary, you can see Annie Peck's paper on the characterizing the binary. And I actually have both my websites there because I have my paper and Annie's pinned on the front page for easy access. Okay, so like I said, this planet is around a tight spectroscopic binary. It is actually the closest image planet to its host binary at about 60 AU. And as you can see here in this plot, so we have orbital distance here and mass. It is not only kind of the closest circumbinary planet in an orbital distance space, but it is well below the brown dwarf mass threshold. So Jason said this, and I don't think he remembers saying this, but it is a very planety planet. Oh, yes, and we hope to get more data, maybe with gravity, for example, to get a good characterization of both the planet and the binary's orbit. So we can look for clues like mutual inclination of the orbits to get some idea of its formation history. All right, this is the GPI and NERC2 spectrum of the new planet. In blue, we have GPI data, and we have the red NERC2 photometry. This is a fairly cool planet for how young the system is at 1050 Kelvin. It is also fairly small, right at 6 Jupiter masses. So I really like GPI data, but unfortunately, it's not necessarily the most exciting in terms of resolution. So we hope to get more robust spectra, maybe with JWST, so that we can see if there's any clues molecularly about the planet's formation that we can tease out. And answer the question, hopefully, is circumbinary planet formation different than around single stars? Okay, so in conclusion, we found the second GPI planet 10 years later, HG 143.811 ABB. It is the closest image planet around a binary. Hopefully follow-up will help us understand planet formation around binaries. I've also talked about my work in vetting the GPI candidate sample. There are a few more candidates that are at that yellow light, so I hope you'll stay tuned for that. And of course, we want to understand these final results because GPI 2 is coming. So while I answer questions, please take a picture of this, fill out the form, join us. I have little flyers, Briley does as well. So yeah, please join us. Thank you.
So really impressive. How important is the forward model match filtering to prying out the detection? If you just use vanilla clip, do you get a sort of signal, or do you really need the FMMF to be able to get a clear detection?
So yeah, I've been using PyClip, which has this FMMF algorithm built into it. So actually, the data that I've been working through, JB at some point in the history of GPI had already run this reduction. And so I was just kind of doing my own very careful extraction with PyClip to make sure we're understanding what was detected from the algorithm.
One more quick question.
I'll go. I have a quick question.
Yes.
Hi, Caitlin Horston from Caltech. Great talk. I was wondering if you had any plans for maybe the far future for the objects that were part of the survey that were below the 7 sigma, and if you think there's hints of anything interesting in there. Obviously, for timing purposes, it makes sense to narrow it down to the highest signal-to-noise objects, but.
Yes, okay, so part of it also was this 300 number of detections. These were from all epochs. So multiple observations of the same planet could have different signal to noise. So actually something like this planet, for example, sometimes when I went back and compared from an earlier epoch, it was one of those lower signal to noise detections. So I think we'll see. I think Bruce will probably convince us that it's time to be focused on GPI 2, right?
Okay, let's thank Nathalie again.